Hello all, this is Emil Naruto. Welcome to my channel. So today I'm gonna explain support vector machines. This is an approach which we actually use for the classification problems. So today I'm gonna explain all the topics and all the subtopics of support vector machines. So first of all, we're gonna look for this particular what is meant by a hyperplane and and then how to using this particular hyperplane, how to classify a data point whether it belongs to a particular class. We're gonna look for that, and after that we will go to explore this particular topic like maximal margin hyperplane, and using this particular maximal margin hyperplane, how to classify any data point, and using this particular maximal margin hyperplane, how to build a maximal margin classifier we're gonna look for. And then we're gonna look for what is meant by a support vector classifier, and then what is meant by support vector machines finally. And after understanding all these topics, we're gonna look for what are all the applications in which we use support vector machines. So these are all the agenda. This is the specific agenda for now we're gonna look for. And but before deep diving into these topics, let's have a look at this amazing quote from ML Naruto. A smile is the easiest way out of a difficult situation. So the meaning of this particular quote is nothing but we usually face so many problems from the from the day one itself from the day one itself when we step onto this planet. From the first day of the from the first day when we step onto this planet, we usually face so many troubles or so many lots of problems. But one easiest way is nothing but just wait. Don't just run. Just wait and just take a long breath and just smile. So, but what happens? You may ask a question like, what happens when you smile? All these problems will may disappear or what? You can say like this. But what I say is, you will get some kind of maturity and some kind of inner strength. If you smile, then you'll automatically develop yourself a kind of inner strength that will come within you, right? So with the help of that particular inner strength, you can understand the situation and you can analyze the situation better, so you can just face the situation with lot more guts and lot more maturity. So this is the particular meaning of this particular quote. Nothing but smile is the easiest way out of a difficult situation. Whatever maybe the situation is, we just need to smile and just move on and let the karma handle its own work. Okay. So yeah, I'm gonna explain now. Let's deep dive into this particular topic. Okay, so first of all, yeah, so let's have a look at here. So first of all, what is mean by a hyperplane? We are going to look for this. Let me select my pen. So first of all, what is mean by a hyperplane? We want to understand this particular term. What is mean by hyperplane? Okay. So hyperplane is nothing but a okay. So just before explaining this particular topic, hyperplane, I just want to give a brief introduction about the SVM. What is mean by an SVM? So SVM is nothing but, first of all, SVM is, it's a kind of approach to solve classification problems. It's a kind of approach to solve the classification problems. Okay. So, and how do we solve a classification problem using this particular algorithm SVM? So further, if you want to understand the algorithm SVM, then for that you need to understand a few terms. Like the first term is nothing but the hyperplane. So first of all, you need to understand what is meant by hyperplane. Hyperplane. So okay, I'm just moving to the next slide. Okay. So what is meant by a hyperplane? For example, if I have a particular let's say, sorry, if I have a feature space, this is nothing but the dimension space. For example, you will get the data in terms of rows and columns, right? So you'll have the rows and you will have the columns both, right? So this is nothing but this x-axis and this y-axis is nothing but these are all the dimensions, right? So these are all the dimensions. This is not a particular x-axis and y-axis. So this is nothing but this is the dimension. Let's say this is x1 and this is x2, right? So these are all the dimensions. So if we have like this, if we have a dimension space like this, so what happens then? Let me change my color. See, I have few data points lying over here. Okay, and also I have some more data points lying over here that is on the same dimension space, right? So and if I ask you to separate, okay, if I ask you to separate this particular data points, how do you separate? How there are how many, I mean, in how many ways you can separate? One way is nothing but I can draw a simple straight line here. By this particular straight line, you can separate both the data points, both the category of the data points, right? Because these are all the data points which are in a color red. Okay, let's say I can call them as let's say I can call them as orange. Okay, orange, and I can call this particular data as apple. Okay, let's imagine we have a data which is related to the fruits, right? Fruits. So I have some data points, particular data points that are belong to this particular category which is orange, and I have some data points which are belong to this particular category that is nothing but the apple. So what happens is, and I just want to separate, I just want to classify, I just want to categorize these particular two categories. How can I do that? So with the help of just a single straight line, I can easily divide this particular two classes as the two different categories. This is the orange category and this is the apple category. Okay, so if I divide this particular problem, if I classify this particular problem like this, then what you can call this particular straight line, this particular straight line is nothing but the hyperplane. So this particular straight line is nothing but the hyperplane. So what is the meaning of the hyperplane? Hyperplane is nothing but it is used to categorize. It is used to divide. Okay. For example, I can explain now. So hyperplane is nothing but if we have a p-dimensional space. Okay. Why I am writing this particular term p-dimensional space? Why? Because see here we have the dimensions 2 here, that is x1, and this is the x2. But I am saying p-dimensional space, that's nothing but it's a generalized form, right? For example, what if you have n number of dimensions, that is you have x1, x2, x3, x4, and so on. See, this is the two-dimensional space. For that, we have imagined a situation like this. But what if we have so many number of features like x3, x4, x6, x7, and so on? We can't even imagine, right? So we can't even imagine the shape of this particular classification. So I'm just taking this particular term as p-dimensional. P-dimensional is nothing but x1, x2, and so on, comma, let's say x xn, right? So we have so many number of features, and with this particular with all these features we have formed a p-dimensional space, right? P-dimensional space. If we have a p-dimensional space, this is called as a dimensional space, or we can also call it as a feature space. We can also call it as a feature space. So if this is a feature space, then our hyperplane is nothing but a subspace. See here, in this entire feature space, our hyperplane is only occupying this particular portion, right? So this is nothing but the subspace. See, out of all the feature space, our hyperplane is actually occupying this particular place only. So this is nothing but a subspace, and whose dimension is one less than that of the p-dimensional space. For example, I can explain you. Wait, I'm just moving on to the another slide. See here, I'll explain. Okay, see here, I'm just explaining here. That's nothing but, for example, uh, let's say, let's say, okay, let's say, mm, I have a, let's say I have a 2D space. Okay, what is meant by 2D space? 2D space is nothing but this particular axis is x1, this particular axis is x2. See here, if I have a 2D space like this, then our hyperplane would be of p minus 1 dimension, that is p minus 1. See here, here what is the value of the p? P is nothing but the 2, right? Why? Because this particular 2 dimension, right? This is nothing but the value of the p. So if a value is the p, then what is meant by p minus 1? P minus 1 is nothing but 2 minus 1, right? So our hyperplane will be of one-dimensional subspace. One-dimensional subspace. How? How? Because see here, if I have this particular two-dimensional space, then this would be my hyperplane, right? So I'll explain another example. Like, for example, if I have a three-dimensional space, like, see here, x1, x2, x3. So I have this particular three-dimensional space. Then what will be my dimension of this of the hyperplane? For example, here what is the p-value? P-value is nothing but the 3. Why 3? Why? Because see, I am saying here we have a three-dimensional space. So that particular 3D is nothing but the our p-value. So this implies what is the value of the p minus 1? P minus 1 is nothing but 3 minus 1, right? That is nothing but 2. So our hyperplane belongs to this particular two-dimensional subspace. So I can draw a subplane, a hyperplane like this. Uh, See here, this is a kind of two-dimensional subspace, right? See, when you look at here, it's just in the shape of a one line, one single straight line, right? So this is in the linear form. Like how can I say? Like this is in just a one-dimensional form. When you look here, here we only have the two-dimensional space. So when we have that particular dimension, I mean these particular dimensions, so our hyperplane will be one less than this particular dimension. So if I have two-dimensional space, then our hyperplane will be 2 minus 1 is nothing but one-dimensional space. I mean, this is our shape of the hyperplane, right? This is the dimension of our hyperplane. For example, if we have the three-dimensional space, then what happens? P minus 1 is nothing but 3 minus 2. That's nothing but the 2. So 2D subspace. Our hyperplane will be of this particular shape. For example, what if we have four-dimensional space? What if we have four-dimensional space? Can you imagine this? Let's see here, like this, like this, like this, like this. We have a four dimensions. Can you imagine the particular shape of this particular hyperplane? We can't even imagine, I think. Why? Because it's more critical when you are actually surpassing each of the dimensions. See here, if you look at this particular two dimension, it would be very easy to draw a hyperplane here. Why? Because this is just as simple as the straight line, right? When you look at here, this is a 3D space, so it would be somewhat difficult, but we can finally draw a hyperplane which is in the form of a 2D space. Okay, but in the 4D space, yes, it's possible to draw, but actually, it would be uh, very ambiguous. So you'll get confused with all these particular increasing in the dimension space. So just remember whatever may be the dimension is. For example, if it is 4D, if it is 5D, or and so on, whatever may be the dimension is, our p value will be that particular dimension. For example, here, what is the dimension space? What is the feature space? Feature or dimension is nothing but both are the same, right? For example, I can call it as a feature space, or I can call it as a dimension space. I can call it as whatever I want. But the usual notation is feature space and dimension space. Okay. So you can call whatever you like. You can call it as dimension space, or you can call it as a feature space. So I'm just here calling it as a dimension space. See here, what is the number of the particular dimension space? This is the 4D. So our p-value will be that. So our p-value will be 4. And what is meant by p minus 1? What is the value of the p minus 1? So here 4 minus 1 is nothing but 3, right? So our hyperplane, so our hyperplane will have this particular 3D subspace. That is, our hyperplane will be actually occupying this particular 3D subspace in the entire dimension space. For example, I can draw this as for example like this. Let's just imagine like this. It's a kind of hyperplane which is actually visible in the in a 3D subspace format, right? If we have a 2D space, our hyperplane will be of 1D subspace. If we have a 3D space, then our hyperplane will be of 2D, two-dimensional subspace. If I have a 4D subspace, then our hyperplane will be of the 3D, three-dimensional subspace. So whatever may be the dimension is, our hyperplane will be one less than that particular dimension. This will be the formula. If I have the p-dimension subspace, then our hyperplane will have this p minus 1 subspace. This will be the ultimate formula. So this is the definition of this particular hyperplane. So I have already explained this particular hyperplane definition, and I'll explain you the problem, right? For example, I have a data point like x is equal to x1, x2, and so on, comma xp whole to the power of transpose, right? So I have a data point. For example, I have a data point. This data point is belong to this particular matrix, you can call. Okay, this particular matrix. But here, let's see. Here it's saying actually the transpose, right? If you say this transpose, then it will be a vector. It will be in the format of the vector like x1, x2, and so on, xp. So this will be in the format of this. Why? Because here we are actually saying the transpose. Transpose is nothing but the alternative set. For example, if we are actually seeing these particular rows, then we need to mention all these rows as the columns. So this will be the structure of this transpose. See, I have a data point. Okay, these are nothing but our data point. Okay, we have a data point in all of these particular vector. Okay, vector we can call it as. So we have a data point in our subspace, in our p-dimensional space. We have a number of dimensions. Let's say we have a p-dimensional space, and we have a data point in our, let's say we have a data point here in our p-dimensional space. Then what happens? Then there is a possibility that this data point will definitely occur on this particular hyperplane. Let's say I some data points right here, and I also have some other data points like here, so on so. Okay, what happens is if our data point belongs to this particular vector, if our data point is belong to this particular vector, then if this data point is also present in this particular dimension, then there may be a chance that this particular data point will definitely lies exactly on this hyperplane. So this is what it is. And what if uh, for example, see here, I have few data points, right? I also have some other data points like this, and suddenly a, a, a data point from my testing data has occurred like this. For example, my data point has occurred here in this particular location. So to which class this particular data point will definitely belong to? That's nothing but we have a kind of procedure for this. For example, uh, we have a function, right? F of x. Actually, f of x star. F of x star is nothing but beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp. This is the function. Function is nothing but, we know, right? Function is nothing but something which takes input variables and something which gives us the output variable. Okay, so if we calculate our function, then it will give some kind of value. Let's say some kind of value, so and so value, some value. Okay, let's say some value. If this particular, okay, see, f of x star, okay, f of x, I can, for the convenience point of view, I can call it as f of x. Okay, if the value of this particular f of x is less than 0, okay, just imagine if f of x value is less than 0, if f of x value is less than 0, then what happens? We can we can easily say that that particular data point, x lies on x lies on one side of a hyperplane. One side of a hyperplane. What does this mean? I'll explain. No worries. See here, let's say okay, so what I'm saying is, if our f of x, if f of x if f of x is less than 0, then this particular x value, will lie on one side of a hyperplane. One side of a hyperplane. That is, for example, if we have already calculated the value of this f of x, right? So we have got something like minus 20, for example. If we have got this particular f of x value is equal to minus 20, then what can we conclude? This particular data point, this red data point is actually belong to this particular data. That is, this red data point, this new data point is actually belong to this blue color data points. Okay, we can conclude like this. For example, if f of x is greater than 0, then our x will lie on another side of hyperplane. What does this mean? For example, we have calculated the f of x, right? And we have got some kind of 200. We have got the value as 200 for this f of x. Then what can we say? Our new data point, this particular, for example, this particular data point is belong to this particular green data points, green class. Okay, I'm naming this particular class as the green. I'm naming this particular class as the blue. Okay, if f of x is less than the 0, then we can definitely say this new data point is actually lying on one side of a hyperplane. This is a hyperplane, right? We can actually say this new data point is actually lying uh, on the blue side of this hyperplane. If f of x is greater than 0, then we can definitely say our new data point is actually lying other side of this hyperplane. That is nothing but it is actually lying on green side of this hyperplane. It's actually lying in the green class. Whereas if f of x is less than 0, we can say this data point is actually lying in the blue class. Okay. So this is nothing but we have actually classified a data point based on this particular value of the function, right? Based on the value of the function, we have already classified a new data point which has just come into our data. Let's imagine this red point is nothing but a test data. Okay, red point is nothing but the test data, test observation we can call. Okay, so for example, test observation, right? So if this I can simply do, there is no scope of getting confused, right? Why? Because see, it's just very simple. I have already explained what is meant by this f of x. F of x value is nothing but, see here, I'm just writing in a box here. F of x value is nothing but beta naught plus beta 1 x1 plus and so on plus beta p xp. So this is the value of the f of x. So I am saying here, if this value is less than 0, if this value is less than 0, then I'm saying this particular data point will actually lie on one side of a hyperplane. No matter whatever may be the side, we can easily say this particular data point is actually lying on this side or this side, whatever. But here actually this particular data point is actually lying on this particular blue region, right? So we can conclude, since f of x is less than 0, so we can conclude this f of x, this new data point is actually lying in the blue region. Okay. For example, if f of x, we have calculated the f of x and we have got some 200 or 300, whatever maybe, it's just greater than 0. Okay. If it is greater than 0, then we can conclude the f of that particular new data point is actually lying on other side of the hyperplane. Let's say this is the hyperplane. It has the two sides, one side, other side. If it is less than 0, it belongs to this side. If it is greater than 0, it belongs to that side. That's how simple it is. So with the help of this particular example, what you can conclude, you have already classified a particular data point successfully, but with the help of all this scenario, I mean, throughout this scenario, what you have observed, one thing that you have observed is nothing but, I can say, I can say, one thing that you need to observe is our hyperplane. Our hyperplane will divide our p-dimensional space, p-dimensional space into equal parts, right? I'll give the particular diagram of this particular statement. What I'm trying to say is, if this is your p-dimensional space, right? No matter whatever may be the variables, if you have x1 and if you have x2 and so on, whatever may be the variables it is. For the convenience, I'm just taking two variables. That is nothing but, this is a two-dimensional space. Let's imagine. But this statement is actually applying for any number of dimensions. See here, I am saying p dimensions. P dimension is nothing but, no matter whatever maybe the dimension is. That is, no matter if it is 3 dimension, 4 dimension, 5, and so on. No matter. But our hyperplane will definitely divide this particular data into equal parts. See here, we are actually dividing our data into equal parts with the help of a hyperplane, right? This is our hyperplane. So, by the previous example, you need to understand this particular statement. Our hyperplane will actually divide our p-dimensional space into equal parts. This will be the conclusion here. Okay, so by this example, you have already understood what is meant by a hyperplane. Now, I just want to explain how do you classify, how do you classify, uh, how do you classify any data point using this particular hyperplane. Okay, yes, I have already explained, but it has some kind of technique here. I'll explain it. Okay, for example, I have I have if a dimensional space. For example, I have a two-dimensional space. Okay, and I have few data points here like this. And I have some red data points here. I need to classify. I need to separate these data points. Okay, one way in which I can separate the data is nothing but I'll just simply draw a simple straight line, right? With the help of this particular straight line, I can easily separate all the data points. I can easily separate all the data points. Okay, but what if? But what if? See here, this is one of many ways. Okay, we have many ways with which we can separate all the data into two equal parts or any equal parts. We have just simply drawn a single straight line. With the help of this particular hyperplane, we have already classified our data as two equal parts. This region is belong to blue region, this region is belong to red region. But how can we divide them in many ways? See here, I'll just draw a line like this. Okay, I can also draw a line like this. Okay, I can also draw a line like this. I can also draw like this. I can also draw like this. So the scope of forming hyperplanes. See here, each line is nothing but a hyperplane, right? So this is a hyperplane. This is another hyperplane. This is another hyperplane. So we are getting some infinity number of hyperplanes here in this particular feature space or dimensional space, whatever it is. So this is one of many ways. We have many ways, so many infinite number of ways we have. But out of all the ways, we are actually dividing the data with just only one way. This is only just one way. Okay, this is one of many ways. This is one of many ways. Okay, but see here, I have drawn all the possible hyperplanes here. Still, I haven't drawn many possible hyperplanes, but the scope of getting, see here, scope of forming hyperplanes, hyperplanes is infinite. See here, why I am saying like this? Why? Because there are infinite number of ways with which we can separate our data. Okay, that's it. And what I'm saying is, for example, if we have a data like this, and see here, uh, okay, I'll take another slide. See, when I'm explaining my class here, you can just simply take this screenshot, right? You can just simply take this as a screenshot, with which you can just by looking at this particular diagram, you will just definitely understand. See, I have a blue region. I also have a green region also. So what do you understand? What do you understand by looking at this particular diagram? Did you develop something? Like see here, I have one region. This is the blue region, and this is the green region. But in between these two regions, we have some kind of gap, right? We have some kind of gap. See here, I have some kind of gap here. This gap will act as a natural classifier, right? If we have some kind of gap between the two categories of data, then that particular gap, this gap, what we can call this gap? This gap is nothing but a hyperplane, right? Hyperplane, what is mean by hyperplane? Hyperplane will what does the hyperplane do? What does a hyperplane do? Hyperplane will just separates the data into equal parts. So this gap is nothing but a natural hyperplane, right? So this gap is nothing but a hyperplane which acts as a natural classifier, which acts as a natural classifier. Why I am saying this particular point is, see here, I haven't drawn any hyperplane manually, right? I haven't drawn or I haven't formed any hyperplane manually. But even if I have, even if I haven't formed any hyperplane manually, this particular data has itself a hyperplane. That hyperplane is nothing but this particular gap. See here, see the gap here, the gap between this particular blue region and this particular green region. We have some kind of gap. This gap is nothing but the hyperplane. This hyperplane is actually acting as a natural classifier. What is the meaning of a classifier? What is the meaning of a classifier? For example, when I given a data, we have some kind of data points. What is the purpose of the classifier? What can a classifier will do? Classifier will just simply splits the data. That is, some part of the data is actually belong to, let's say, green, okay, and some part of the data will actually belongs to let's say, blue. So this job is done by this particular classifier, and here even we haven't formed any kind of manual, hyperplane here. This gap here itself in between these two kind of regions is itself a hyperplane. It's a natural hyperplane which is actually acting as a natural classifier, right? So did you understand? So what happens is, for example, uh, for example, so if I have a natural classifier like this, how can I classify my data? How can I classify my data? If I have a natural classifier like this, how can I classify my data? For example, if I have a data point here, then what can I say? This data point is definitely belong to this particular blue region, right? Why? Because see here, here itself, this particular gap is actually acting as a natural classifier. So even if we haven't formed any kind of hyperplane, we need to imagine that there is some kind of hyperplane in between this gap. Let's see. I will draw some kind of 1 minute. I'll draw something. Mm, let's see here. This particular orange bar is nothing but the hyperplane. It's an imaginary hyperplane which is actually not formed by any human. Okay, this hasn't been created by ourselves. This is actually a natural hyperplane. which is nothing but this particular gap, right? So if I say if I place any kind of new data point here, then definitely this data point is actually belong to this particular class. Okay, and for example, if I place any kind of data point here, then what can I say? This particular data point is actually belonging to this particular class. Why? Because see here we have a hyperplane. All the data points which are lying beside this particular hyperplane are actually belong to one class, and all the data points which are actually lying onto this side of this hyperplane are actually belonging to uh, this particular class. Okay, how can we decide? Mathematically, how can we decide? Is nothing but you already know. I have already explained. We usually calculate the f of x. What is the value of the f of x? F of x is nothing but beta naught plus beta 1 x1 plus and so on plus beta p xp. So this is nothing but the function, right? So this is nothing but the function of our input variables. So these x1, x2, x3 and so on xp are nothing but our features, are nothing but our columns, right? And this beta naught is nothing but our slope here. Oh. So these are all the parameters here. These are all the parameters. So and beta 1 x1, beta p xp and so on. These are all the parameters here. So if I okay, you have finally calculated the f of x. You have finally calculated the f of x, and you have got some kind of value as let's say you have got some kind of 295 value, okay, which is greater than 0. Then what can we say? This particular data point is actually belonging to this particular class. We can consider this, okay. And what if we have f of x? We have calculated f of x and we have got some kind of minus uh, minus 50. Okay, we have got some kind of value as minus 50. Then what can we say? We can easily say this particular data point is actually belonging to this particular class, this particular region. Depending upon the values, I mean depending upon the signs here. See here, greater than 0 is nothing but it's a positive sign, right? Less than 0 is nothing but it's a minus sign, right? See here, it's a positive sign and it's a minus sign. So depending upon this particular sign, we are actually classifying the data points. No matter, for example, you can classify. If I have, you can exchange also. For example, you can allot this particular data point as plus sign, and you can allot this particular data point as minus sign, or vice versa. Whatever you want, you can. But you will just classify based on these two signs. Okay, and instead of just looking at the signs, you can also look at this particular the magnitude here. This is nothing but the value is nothing but the magnitude here. You can look for this particular magnitude. For example, here I have classified, let's say this is plus, and let's say this is minus. Okay, for example, we have calculated our f of x and we have got some kind of 295 value which is greater than 0. So we have classified this particular, we have allotted this particular new data point which is belonging to this particular class. Okay, and now when you look at here the magnitude here 295, which is a far greater than this particular 0, that's nothing but we are actually more confident. Okay, I'll take another slide and explain. See here, we have calculated f of x. Okay, we have calculated f of x and we have got some 295 value, which is greater than 0. And what we can do? for example, in our data we have got some kind of a new point which is actually lying here. Okay, which is actually lying here. So what can we do? What can we do here? We will just look for this particular magnitude, this particular magnitude here. This is nothing but 295, and also besides 295 it is actually saying which is greater than 0. So you will definitely classify this particular data point which is belonging to this particular red region. But here when you look at this particular magnitude here, that is 295, we can say with confidence, we can confidently say that this data point, okay, we can say x, okay, this data point is lying in the red region. The red region. Confidently means what? Confidently means this particular green data point, this particular new data point is actually very far from this particular hyperplane. This 295 value is nothing but the distance between this new data point and this hyperplane, right? Why? Because if I calculate f of x for another data point, which is let's say I have calculated another data point, and which is let's say here I have some kind of another data point which is just placing just beside this particular hyperplane. So I have calculated this f of x for this particular data point. This particular data point I'm calculating this f of x, and I have got some kind of what we can say, let's what can we, let's say minus 0.7. okay, for example minus 0.7, I have got the value. What happens? Which is less than 0. Okay, this is less than 0, but here look at the magnitude here. Okay, with the help of this particular minus sign, we can say this particular data point is actually belonging to this particular region. Okay, but here just look at the magnitude here, 0.7, which is very closer to this particular 0. See here, this data point is actually in a closer position to this particular hyperplane. So we can say, but we can't say confidently. Okay, we are not confident that this data point belonged to any particular class. Why? Because see here when you look at this particular data point, it is actually very far from this particular hyperplane, right? But when you look at this particular data point, it is actually lying in a closest position to this particular hyperplane. So we can't say confidently that this particular data point is actually belong to this particular region, or whether this particular data point is actually belonging to this red region. We can't even say. Why? Because this is lying very close to the hyperplane. So this is a problem. So this is a problem. So due to this reason, we can't even confirm whether this data point is actually belonging to orange region, yellow region, or this data point is actually belonging to this red region. We can't even confirm. Why? Because here you just need to look at the magnitude here. This magnitude is which is very closer to 0. But when you look at this particular magnitude 295, which is very far from the value 0. That's the basic concept here. I'm just moving to the next slide to explain further concepts. Okay, so till now you have understood what is meant by a hyperplane. Okay, till now you have understood what is meant by hyperplane, and you have already understood. Uh, how to classify a data point. How to classify a data point based on this. Sorry. How to classify a data point using this hyperplane. So I have explained these two things, and okay, so this is a very deep concept. So I mean, yes, I can move to the next concept, but I'm not sure whether you can understand many more subtopics of this particular SVM concept or not. Why? Because these each and every concept is actually interlinking. Why? Because when you just say here SVM, what is SVM? SVM is nothing but the generalized form of SVC. SVC is nothing but support vector classifier. SVM is nothing but the support vector machine. Okay. So SVM is nothing but support vector machine, and SVC is nothing but the support vector classifier. So what is meant by SVM? SVM is nothing but the more generalized form of this SVC. But what is meant by SVC? SVC is nothing but more generalized form of maximal margin hyperplane. Maximal margin classifier. Maximal margin classifier. Okay. So what is meant by this maximal margin classifier? Maximal margin classifier. What is meant by this? So maximal margin classifier is nothing but uh, using maximal margin hyperplane, we classify a data point. Right. So these are all the topics which are actually interlinked with each other. So if you want to understand, you need to understand what is meant by this SVC. If you want to understand what is meant by support vector classifier, you need to understand what is meant by this maximal margin classifier. If you want to understand this, what is meant by this maximal margin classifier, you need to understand what is meant by this maximal margin hyperplane. If you want to understand this maximal margin hyperplane, you need to understand what is meant by a hyperplane, right? So these are all the concepts which are actually interlinked. So as of now, I have already explained what is meant by hyperplane, and I have already explained what is meant by hyperplane, and I have already explained how to classify any data point using this particular hyperplane. Okay, so enough of this in this video, enough of the session. Why? Because when I explain two more additional topics, additional subtopics, you will definitely get confused. Why? Because these are all the interlinked concepts. So just focus on these two topics for now, and in the next video I'll definitely explain what is mean by a maximal margin hyperplane, and using this particular maximal margin hyperplane, how can you classify any data point using this particular maximal margin hyperplane, nothing but the maximal margin classifier. Okay, and after that I'll explain what is mean by a support vector classifier. This is nothing but a generalized form of maximal margin classifier, right? So only this will be this, the entire concept of SVM will definitely understand only if you understand what is meant by hyperplane, what is meant by maximal margin hyperplane, what is meant by maximal margin classifier, what is meant by support vector classifier, what is meant by then only you can understand what is meant by support vector machine. Okay, so yes, so that's all for this session. I'll see you in the next video. Good night, take care, Jai Hind.